So we've answered the thing about continuous attributes. Now, here's another thing. When do we really stop?
When we get all the answers right, when all the training examples are in the right category, class.
Right, so the answer in the algorithm is when everything's classified correctly. That's a pretty good answer, Michael, but what if we have noise in our data? What if it's the case that we have two examples of the same object, the same instance, but they have two different labels? Then this will never be the case.
Oh. So then our algorithm goes into an infinite loop.
Which seems like a bad idea.
So we could just say, or we've run out of attributes.
Or we run out of attributes. That's one way of doing it. In fact, that's going to have to happen at some point, right? That's probably a slightly better answer. Although that doesn't help us in the case where we have continuous attributes and we might ask an infinite number of questions. So we probably need a slightly better criterion, don't you think? So what got us down this path was thinking about what happens if we have noise. Why would we be worried about having noise anyway?
Noise anyway. Well, I guess the training data might have gotten corrupted a little bit, or maybe somebody copied something down wrong.
Right. So since that's always a possibility, does it really make sense to trust the data completely and go all the way to the point where we perfectly classify the training data?
But Charles, if we can't trust our data, what can we trust?
Well, we can trust our data, but we want to verify. The whole point is generalization. And if it's possible for us to have a little bit of noise in the data, an error here or there, then we want to have some way to be able to handle that possibility, right?
I guess so.
So what will we do? I mean, we actually have a name for this, right? When you get really, really, really good at classifying your training data, but it doesn't help you to generalize. We have a name for that.
Right. That sounds like overfitting.
Exactly. We have to worry about overfitting.
So you can overfit with the decision tree too?
Yeah. What, you don't believe that?
No. I was being naive. I mean, I know that you can overfit with the decision tree. I was just.
Okay. Yeah, but your is the that you usually give when you're like, I don't believe what you just said, Charles, but I'm gonna go along with it anyway because I have to get off the phone soon.
Fair enough. I'll try to have a different personality then.
Okay, that's step one. Have a different personality with maximal information gain. Okay, so we don't want to overfit. So we need to come up with some way of overfitting. Now, the way you overfit in a decision tree is basically by having a tree that's too big. It's too complicated, right? Violates Occam's razor. So what's a kind of, let's say, modification to something like ID3 to our decision tree algorithm that will help us to avoid overfitting?
Well, last time we talked about overfitting, we said cross-validation was a good way of dealing with it, which allowed us to choose from among the different, say, degrees of the polynomial.
Right.
So maybe we could do something like that. I don't know, try all the different trees and see which one has the lowest cross-validation error. Maybe there's too many trees.
Maybe, but that's a perfectly reasonable thing to do, right? You take out a validation set, you build a decision tree, and you test it on the validation set, and you pick whichever one has the lowest error on the validation set. That's one way to avoid it. And then you don't have to worry about this question of stopping. You just grow the tree on the training set minus the validation set until it does well on that, and you check it against the validation set, and you pick the best one. That's one way of doing it, and that will work perfectly fine. There's another way you can do it that's more efficient, which is you do the same idea of validation, except that you hold out a set, and every time you decide whether to expand the tree or not, you check to see how this would do so far in the validation set. And if the error is low enough, then you stop expanding the tree. That's one way of doing it.
So is there a problem in terms of, I mean, if we're expanding the tree depth first search wise, we could be looking at one tiny little split on one side of the tree before we even look at anything on the other side of the tree.
That's a fine point. So how would you fix that?
Maybe expand breadth first?
Yeah, that would probably do it. Anything else you can think of? Well, so you could do pruning, right? You could go ahead and do the tree as if you didn't have to worry about overfitting. And once you have the full tree built, you could then do you could do pruning. You could go to the leaves of the tree and say, well, what if I collapse these leaves back up into the tree? How does that create error on my validation set? And if the error is too big, then you don't do it. And if it's very small, then you go ahead and do it. And that should help you with overfitting. So that whole class of ways of doing it is called pruning. And there's a whole bunch of different ways you might prune, but pruning itself is one way of dealing with overfitting and getting you a smaller tree. And it's a very simple addition to the standard ID3 algorithm.